Welcome to the video guys. In this video we're going to discuss about chapter 2,
which is magnetic force field. In previous lesson, we learned about magnetic force. Now let's discuss about magnetic force field. The first part of magnetic force field is
how to find the magnetic flux density at a point in a magnetic field formed around a current carrying conductor. To find the magnetic flux density at a point in a magnetic field formed around a current carrying conductor, we use Biot-Savart's law. Let's consider a wire. This is a current carrying conductor. And there is a point here. Let's take this point as P. And we need to find the magnetic flux density at this point due to magnetic field formed around the current carrying conductor. In this conductor, flowing current is I. We're going to look at the element of a conductor. Element, let's take is as the element of the conductor. Let's take it as delta L. We're gonna find the magnetic flux density at the point P. The magnetic field formed around this delta L part, and we'll draw a line, straight line to the point P. And this P, the length distance between delta L and P, we'll take it as R, and the angle between the current conducting wire and the P, current carrying wire and P, is theta. We'll take that as theta. Let's derive an equation. Here the delta magnetic field, magnetic flux density, directly proportional to I, and delta B is directly proportional to delta L, and the delta B is directly proportional to sine theta, and also the delta B is directly proportional to 1 over distance squared. This delta B is the magnetic flux density between the delta L, in the place delta L. If we combine these and let's form a formula. Let's combine these and let's form a formula. Delta B is directly proportional to I delta L sine theta divided by distance squared. And we'll take this as delta B equal to K, which is a constant, I delta L sine theta divided by R squared. And we can represent K as, K is equal to mu naught divided by 4 pi, and this mu naught is magnetic permeability of free space, permeability of magnet. We'll substitute permeability mu naught divided by 4 pi to this equation, and let's write the formula. Delta B equals mu naught divided by 4 pi into I delta L sine theta divided by R squared. We use this formula to find the magnetic flux density at a point in a magnetic field formed around a current carrying conductor. Delta B equal mu naught divided by 4 pi into I delta L sine theta divided by R squared, and this is Biot-Savart's law. If we need to find the direction of magnetic flux density, we can use right-handed corkscrew rule. We already learned this in chapter 1. Now let's look at derivations from Biot-Savart's law. There are 4 derivations. There are magnetic flux density at a point around a very long straight conductor. And the next one is magnetic flux density at a center of a flat circular coil of a wire carrying conductor. And the third one is the magnetic flux density along axis of a solenoid carrying a current. The fourth one is magnetic flux density along a toroid carrying a current. Let's consider this as a wire which is very long, and this is the point we're going to measure the magnetic flux density. And let's draw a straight line. This point is point P. Angle between the wire and the point is 90 degrees because the straight line. Distance between the point P and the wire is R. The magnetic flux density at point P due to current passing through the whole conducting wire can be derived by using mathematical integration for Biot-Savart's law expression, and which can lead to an expression of magnetic flux density at the point P is B equal mu naught divided by 4 pi into 2I divided by R. If we simplify this expression, mu naught divided by 2 pi R into I. Magnetic flux density at center of flat circular coil of a wire carrying a current. Let's consider this as a wire, which is a circular wire coil. This is the current carrying direction. This is I, and this distance between the center of the coil and the radius R. Let's take this as distance between them, R radius, and this is the part which the magnetic field acts. We'll take this as delta L. Now let's write the expression. Delta B is equal to mu divided by 4 pi into I delta L, and we'll use sine 90 divided by R squared. We use sine 90 here. The angle between the wire, this one, wire and the center is 90 degrees. Therefore, we use sine 90 here. Normally, magnetic field pass through the plane either upwards or downwards
in a circular coil.
We can use right hand corkscrew rule or right hand grip rule to find the direction of magnetic field lines. If we want to find the resultant magnetic flux density at the center of the coil, we should multiply the current elements. This delta L is the current element. Let's write it down. Delta B equal to sigma delta B sigma mu naught divided by 4 pi I into delta L. Sine 90 is 1 divided by R squared. Only the current element changes here. Therefore, we can write this as B equal mu naught divided by 4 pi into I divided by R squared into sigma delta L. We should multiple current elements to find the magnetic flux density. If there is n number of turns, we can write the expression as this: B equal mu naught divided by 4 pi into I divided by R squared. The whole circle is 2 pi R and number of turns equal n into n. If we simplify these, mu naught into Ni divided by 2R. show this r and r squared cancel off, 2 pi divides and 2 is 2. Third one is magnetic flux density along the axis of long solenoid carrying a current. It's the direction of current in, and this is outward current direction, and this is south pole and this is north pole, and this is the direction. Using Biot-Savart's law, it can be proved that the magnetic flux density along the axis can be given as B equal mu naught N I. This N can be represented as number of turns N divided by length of the solenoid. Now we are going to look at the magnetic flux density along axis of toroid carrying a current. This is the toroid. A wire, current carrying wire, is looped around a circular thing, and this is the current I inwards and this is the current outwards. This is the current part is the current carrying conductor. For this also we use the same expression as we used for solenoid. B equal mu naught N divided by I, and this N is N divided by 2 pi r. Here L, we use L, here 2 pi r. Now let's discuss about forces between two parallel conductors carrying current. We can consider in two situations, there's two parallel conductors carrying current in same direction. If they carry current in same direction, and then the opposite direction. This is a current carrying wire and which carry current in the same direction. Forwards, this is also carrying current in the upward direction, and this is I1 and this is I2. Magnetic forces between the two conducting wires will be attractive force. They will be attracted. There will be a force towards the center. They will attract. And if the conducting wires are traveling in opposite direction, this is traveling downwards and this is traveling upwards, and this is I2 and this is I1, they will repel each other. They will repel there, they will attract here. Same direction they will attract, opposite direction they will repel. And this is the cross-sectional view of the wires carrying in this current carrying in the same direction and the opposite direction. Here current is moving out of the plane. Here also current is moving out of the plane. If we use right hand grip rule, the magnetic field will be moving in anti-clockwise direction, and here also anti-clockwise direction. Magnetic fields will be moving in anti-clockwise direction. Let's look at this direction. It is moving into the plane and this is moving out of the plane. And if we use right hand grip rule here, the magnetic fields will be anti-clockwise here and clockwise here. Therefore, there will be a gap between them. The magnetic force will repel each other. Here they travel in clockwise direction, both get attracted. Here one clockwise, another one anti-clockwise. Therefore, they get repelled. In this region, there will be a strong field attraction. In this part, there will be a weak field attraction. Consider two parallel wires moving in the same direction. Force in the current carrying wire I1 will be mu naught I divided by 2 pi r. If we consider the force on current carrying I2, conductor of I2, to will be F equal B I L. Here the force acting, the magnetic force acting by the other wire, which is this one, mu naught into I divided by 2 pi r, this is I1 and this is also I1, into I2 into the L, the part which acting on it. So I1. If we consider I2 also, the similarly BFI2, there will be a force on I1, sorry, I2 divided by 2 pi r. This is the force acting on I1, current carrying wire I1. BIL mu naught into I2 divided by 2 pi r. This one 2 pi r into I1 into L. Hence the force on the common length of both conductors due to the current flowing in them is, we can write a common expression for them, F equal mu divided by 2 pi I1 into I2 into L divided by R. And also we can find the force per unit length by mu naught divided by 2 pi into I1 into I2 divided by R. And that's all for chapter 2. If you want chapter 3, which is torque acting on a current loop, drop a comment. Thanks for watching.